This episode is brought to you by Cisco Educational Premium.
Planck units such as those of time and length are many orders of magnitude too large or too small to be of practical use. So that Planck units as a system are typically only relevant to theoretical physics. In some cases, a Planck unit may suggest a limit to a range of physical quantity where present-day theories of physics apply. For example, our understanding of the Big Bang does not extend the Planck epoch, that is, when the universe was less than 1 Planck time old. Describing the universe using the Planck epoch requires a theory of quantum gravity that will incorporate quantum effects into general relativity. Such a theory does not yet exist. Several quantities are not, and I quote, extreme in magnitude, such as the Planck mass, which is about 22 micrograms, very large in comparison with subatomic particles and within the mass range of living organisms. Similarly, the relative units of energy and momentum are in the range of some everyday phenomena. Planck units have little anthropocentric arbitrariness, but do still involve some arbitrary choices in terms of the defining constants. Unlike the meter and second, which exist as base units in the SI system for historical reasons, the Planck length and Planck time are conceptually linked at a fundamental physical level. Consequently, natural units help physicists to reframe questions. Frank Wilczek puts it succinctly: we see that the question is not why is gravity so feeble, but rather why is the proton's mass so small. For natural Planck units, the strength of gravity simply is what it is, a primary quantity, while proton's mass is the tiny number 1 on 13 quintillion. While it is true that the electrostatic repulsive force between two protons alone in free space greatly exceeds the gravitational attractive forces between the same two protons, doesn't about the relative strength of the two fundamental forces. From the point of view of Planck units, this is comparing apples with oranges, because mass and electric charge are incommensurable quantities. Rather, the disparity of magnitude of force is a manifestation of the fact that the charge on the proton is approximately the unit charge, but the mass of the protons is far less than the unit mass. In particle physics and physical cosmology, the Planck scale is an energy scale around 1.22 times 10 raised to 19 gigafolds. The Planck energy corresponding with the energy equivalent of the Planck mass is 2.17645 times 10 raised to negative 8 kilogram, at which quantum effects of gravity become significant. At this scale, present description and theories of subatomic particle interactions in terms of quantum field theory break down and become inadequate due to the impact of the apparent non-renormalization of gravity within current theories. At the Planck scale, the strength of gravity is expected to become comparable with the other forces, and it has been theorized that all the fundamental forces are unified at that scale. But the exact mechanism of this unification remains unknown. The Planck scale is therefore the point at which the effects of quantum gravity can no longer be ignored in other fundamental interactions, where current calculations and approaches begin to break down, and a means to take account of its impact is necessary. On these grounds, it has been speculated that it may be an appropriate lower limit at which a black hole could be formed by collapse. While physicists have a fairly good understanding of the other fundamental interactions of forces on the quantum level, gravity is problematic and cannot be integrated with quantum mechanics at very high energies using the usual framework of the quantum field theory. At lesser energy levels, it is usually ignored, while for energies approaching or exceeding the Planck scale, a new theory of quantum gravity is necessary. Approaches to this problem include string theory and M theory, loop quantum gravity, non-commutative geometry, and causal theory. In Big Bang cosmology, the Planck epoch or the Planck era is the earliest stage of the Big Bang before the time passed was equal to the Planck time, or approximately 10 raised to negative 43 seconds. There is no current available physical theory to describe such short times, and it is not clear in what sense the concept of time is meaningful for values smaller than the Planck time. It is generally assumed that quantum effects of gravity dominate physical interactions at this time scale. At this scale, the unified force of the standard model is assumed to be unified with gravitation. Immeasurably hot and dense, the state of the Planck epoch was succeeded by the grand unification epoch, where gravitation is separated from the unified force of the standard model, in turn followed by inflationary epoch, which ended after about 10 raised to negative 2 seconds, or about 10 raised to 11 Planck time. After the measurement of the cosmological constant in 1998, estimated at 10 raised to negative 122 in Planck units, it was noted that this is suggestively close to the reciprocal of the age of the universe squared. Barrow and Shaw propose a modified theory in which the cosmological constant lambda is a field evolving in such a way that its value remains lambda equivalent to the age of the universe squared through the history of the universe. The Planck length, denoted Lp, is a unit of length defined as Lp is equivalent to root of reduced Planck constant G on C raised to 3. It is equal to 1.6162518 times 10 raised to negative 45 meters, where the two digits enclosed by parentheses are estimated standard error associated with the reported numerical value, or about 10 raised to negative 20 times the diameter of a proton. It can be motivated in various ways, such as considering a particle whose reduced Compton wavelength is comparable to its Schwarzschild radius. Though whether those concepts are in fact simultaneously applicable is open to debate. The same heuristic argument simultaneously motivates the Planck mass. The Planck length is a distance scale of interest in speculation about quantum gravity. The Bekenstein-Hawking entropy of a black hole is 1/4 area of its event horizon in units of Planck length squared. Since 1950s, it has been conjectured that quantum fluctuations of the space-time metric might make the familiar notion of distance inapplicable below the Planck length. This is sometimes expressed by saying that, and I quote, space-time becomes a form at the Planck scale. It is possible that the Planck length is the shortest physically measurable distance, since any attempt to investigate the possible existence of shorter distances by performing high energy collision will result in a black hole production. High energy collision, rather than splitting matter into finer pieces, would simply produce bigger black holes. The strings of string theory are modeled to be on the order of the Planck length. In theories with large extra dimensions, the Planck length calculated from the observed value of G can be smaller than the true fundamental Planck length. The Planck time, Tp, is the time required for light to travel a distance of 1 Planck length in a vacuum, which is a time interval of approximately 5.39 times 10 raised to negative 44 seconds. No current physical theory can describe time scale shorter than the Planck time, such as the earliest events after the Big Bang. Some conjecture that the structure of time need not remain smooth at intervals comparable to the Planck time. The Planck energy EP is approximately equal to the energy released in the combustion of the fuel in automobile fuel tank, 57.2 liters at 4.2 megajoule per liter of chemical energy. The ultra energy cosmic ray observed in 1991 had a measured energy of about
50 joules equivalent to about 2.5 times 10 raised to negative 8 Planck energy. Proposal for theories of doubly special relativity posit that in addition to the speed of light, an energy scale is also invariant for all inertial observers. Typically, this energy scale is chosen to be the Planck energy. This episode is brought to you by Cisco Educational Premium.
Epoch of the universe known as the Planck epoch occurred at 10 raised to negative 43 seconds. During this time, it is believed that all the fundamental forces, including electromagnetism, the weak force, the strong force, were unified as one grand unified force at this point. However, it is important to note that this isn't exactly t is equal to 1, as we want to avoid the singularity. The state of the universe at this epoch and what happened before it remain unknown. The earliest time we can theorize about is the period of inflation, which occurred from about 10 raised to negative 36 seconds to about 10 raised to negative 33 seconds after the Big Bang. During this time, whatever existed prior to inflation experienced rapid exponential expansion, faster than the speed of light. This is allowed because there is no theoretical restriction on the speed at which space itself can expand. It expanded from a point to a point about the size of a baseball. You might wonder how this is even possible, since we know that nothing can travel faster than the speed of light. While this is true for information transfer, cosmic inflation involves the expansion of space itself, allowing distant points to move away from each other faster than light can travel between them. Most of our current understanding comes from the period after inflation. So the accurate way to view the Big Bang is not as a single point of origin, but as a period when the early universe was extremely hot, dense and rapidly expanding. Thus the Big Bang is a description of everything that occurred after t is equal to 1. Inflation is believed to have occurred from 10 raised to negative 36 to 10 raised to negative 3 seconds. The energy source behind this rapid expansion and cosmic inflation erased any information about what existed before it. The theory of the standard model of cosmology is well understood, starting at about 10 raised to negative 12 seconds, as the universe's energy levels can be reproduced in current particle accelerators. Before this time, we can only speculate about the events. From about 10 raised to negative 3 seconds to 10 raised to 12 seconds, strong force and electromagnetic and weak forces, collectively known as electroweak force, was still unified. The origin of the initial massless fundamental particles is uncertain. They might have condensed from the energies present during the Big Bang, or an inflation field containing inflations could have decayed into the fundamental particles we observe today. Around 10 raised to negative 11 seconds, the temperature drops further to 10 raised to 15 Kelvin, marking the beginning of the quark epoch. The electromagnetic and weak forces begin to separate, leading to electroweak symmetry breaking. The X fields gains non-zero potential, imparting mass to the fundamental particles of the standard model. At this point, the essential components of atoms are in place, and the universe temperature is around 1 quadrillion Kelvin. As the universe continues to expand and cool, the extremely high temperatures present prevent quarks from combining into hadrons like protons and neutrons. However, as temperature drops to about 1 trillion Kelvin at 10 raised to negative 5 seconds, the quark plasma transitions into a hadron gas consisting of protons
neutrons, and certain mesons, which eventually decay into photons and electrons. As the temperature further decreases, particles and antiparticles begin to annihilate, resulting in lighter particle-antiparticle pairs, such as neutrinos and photons. Interestingly, there is a slight asymmetry in this process, which with more particles being generated than antiparticles, leading to the survival of certain quarks and electrons. This enables the formation of protons, neutrons, and electrons, which are essential for creating the initial atoms. The annihilation process culminates with the Lipton epoch, which occurs around 1 second mark when the temperature subsides to about 5 billion Kelvin. During this epoch, leptons conclude the annihilation process. Following this remarkable display, the majority of the matter particles transforms into photons and neutrinos. However, due to the matter-antimatter asymmetry, a small quantity of protons, neutrons, and electrons remain surviving as the fundamental building blocks for atoms. At around a few minutes after the universe's inception, the epoch of the Big Bang nucleosynthesis (BBN) begins with protons and neutrons produced in equal numbers. Free neutrons are inherently unstable and undergo beta decay, transforming into protons over approximately 10 raised to 50 minutes. As the temperature remains high, proton-neutron conversion is balanced by neutron-proton conversion. But as the universe cools further, neutron decay becomes more prevalent. Free neutrons strive to join other hadrons and form more extensive nuclei before decay, leading to the universe consisting of about 75% hydrogen nuclei and 25% helium-4 nuclei, along with small amounts of deuterium, helium-3, and trace quantities of lithium-9 nuclei. In this period, the environment predominantly consisting of ionized nuclei without bound electrons. The formation of neutral atoms requires electrons to attach to positively charged nucleons to achieve charge balance. However, the universe is still scorching and electrons can only briefly adhere to nucleons before being forcibly separated due to their immense energy. As a result, the universe remains opaque and photons carrying light continuously interact with nucleons and electrons, hindering their free propagation through space. This photon epoch lasts for about 390,000 years until the universe cools down to 3000 Kelvin. At this point, electrons possess significantly reduced energy, allowing the electromagnetic force to permanently bind them to nucleons, leading to the formation of stable neutral atoms in a process called recombination. As a consequence, photons are no longer confined amidst the chaos of positive nucleons and negative electrons. They are now free to traverse the universe. If an observer was present in space, he or she would be able to observe this light. Today, the first light of the universe, known as the cosmic microwave background (CMB), can be perceived in all directions. This light was emitted during the formation of stable neutral atoms, providing us with valuable insights into the early universe and the origin of atoms. Atoms constantly interact. However, to comprehend this, we must first determine the definition of interact. Our typical understanding of interaction is based on the macroscopic world. I place my palm on the chair. My palm interacts with the chair. You step on the floor, you interact with the floor, and so forth. In these instances, one solid boundary or surface interact with another solid boundary or surface. Nevertheless, our macroscopic understanding becomes less applicable at a microscopic level, which lead to confusion about interaction. If we could magnify the scale to atomic level, we would witness a chaotic envisionment. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.